The first thing we'll need to do is to build the original circuit. The original circuit, not the equivalent circuit. We need to build the
original.
Yeah, the original circuit first. Okay, so R1 here, R2 is 220, and then R3 is 100 ohms. 100 ohms, and then the current source. The current source is in series with R3, and the voltage source is in series with R1. Yep. And US is 10.2 volts, so we change it to 10.2 volts. And IS still 20 milliamperes. Okay. And then make the rest of the connection. And then the first thing we'll need to measure is the voltage, the open circuit voltage of this one port network, right? So we use the voltage source, the voltage meter here, in parallel with A and B, and then we can power it on. Okay. Still fluctuate.
Oh, it's fixed.
Okay, the open circuit voltage is 5.95. You may get like 6.17 or 6.30. Both is correct because the internal resistors in your circuit may have some difference between to my circuit. And then we put down the 5.94 to this line UOC here, and then we remove all the sources. Change the voltage source to a wire, and then change the multimeter to ohms. Okay, so the equivalent resistance is 153.2 ohms. So we can put down this value to this length. And the short circuit current can be derived by UOC divided by RI. It's a value around 37 or 38 or 40 milliamperes. It depends on your circuit. Okay. We have finished the table 1-5, and then the table 1-6. We plug the current source back. The voltage source back. And power it on. And then find the load here. 10 kilo ohms resistors.
Very resistor.
And connect it to to connect the load to the one-port network. Okay. And then oh, I missed this one. We have some recommendations in our circuit like 2 milliamperes, 8 milliamperes, and 15 milliamperes, 25 milliamperes. So what we need to do is change the variable resistors and observe the ambient here. Okay, we got 10 milliamperes, and we put down 2 milliamperes in this length and 5.63 volts in this length. And this is the first pair's UI value, and then we change the variable resistors to 8 milliamperes. Yes, 8 milliamperes, and then we put down 8.1 milliamperes in this length, and 4.68 volts in this length. Okay, we got the second pairs of UI value, and then 15 volts. Yes, 15.3 milliamperes in this third length, and 3.58 volts in the third length. So we got the third pair of UI. So the same method to adjust the load resistors to 20. To change it to let this display be
36.
25 milliamperes and 38 milliamperes, and we put down these values in this length. That's the first two rows in this length. We use the original circuit. Okay. So any questions so far about the original circuit?
No.
And then the last two rows we use the equivalent circuit. The equivalent circuit. Okay. We need to change the circuit architecture. And remember, we have measured the open circuit voltage earlier, right?
Yeah.
It's about 5.95. Okay. So we change the voltage source to 5.95 volts, and then the equivalent resistors is actually these two, R1 and R2 in parallel. Okay. And we remove R3. And this is the equivalent circuit. And then power it on. The same method. We adjust the variable resistors to let the current be 2 milliamperes. We put down 2 milliamperes in this length and 5.63 volts in this length, and then change the load to
5.
Yes, let it be 8 milliamperes. 7.8 milliamperes. We put down 7.8 milliamperes in this length and 4.71 volts in this length. So we got the second pairs of the equivalence circuits. The same method we will got the 5 pairs of the equivalence, the equivalent, the circuits. And then after class, we can draw the curves in these subordinate systems. You will find these two curves are actually very near. Yes, based on this Thevenin theorem.
Yes.
Any questions about the previous surveys?
Yeah, good.